Imagine two particles, light years apart, instantly mirroring each other's actions. No signal, no delay, just an impossible connection. This isn't science fiction, it's quantum entanglement, and it's challenging everything we thought we knew about reality. What if this spooky action at a distance holds the key to unlocking the universe's deepest secrets? Quantum entanglement is one of those ideas in science that feels less like something from a textbook and more like something from a science fiction novel. It is a phenomenon so strange, so counterintuitive, and so mysterious that even the greatest minds in physics have wrestled with it for nearly a century. To truly understand its significance, we must begin by stepping into the world of the very small, the world of quantum mechanics, where particles do not behave like the solid, predictable objects we are used to in daily life, but instead exist in a haze of probabilities, potentialities, and interconnectedness that challenges every common-sense notion we have about reality. At its most basic level, quantum entanglement occurs when two or more particles interact in such a way that their properties become linked, no matter how far apart they are later separated. Imagine creating a pair of photons in a laboratory. When they are generated together, their states, things like spin or polarization, become correlated. If you measure one photon and discover that it is polarized vertically, you can immediately predict that the other will be polarized horizontally, even if it has traveled to the other side of the universe. The bizarre part is that this connection seems to exist instantaneously, faster than the speed of light, as though space and time themselves cannot sever their bond. This idea may sound simple when put into words, but the reality is far more unsettling. In classical physics, which governs the large-scale world of planets, cars, and people, objects have properties that are well defined. A coin lying on a table is either heads or tails, not both. A ball moving through the air has a definite speed and position at any given time. But in the quantum world, particles do not obey such straightforward rules. Before measurement, they exist in a superposition of possible states, and only when observed does the particle seem to choose one outcome. Entanglement complicates this further because the act of measuring one particle does not just reveal its state, but also dictates the state of its partner, regardless of distance. This raises profound questions. How can two particles separated by light years coordinate their states with such precision? Is there some hidden mechanism at work? Or is our very understanding of reality incomplete? The mystery of entanglement was first highlighted in the early 20th century when quantum mechanics was still being formulated. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper now known as the EPR paradox. They argued that quantum mechanics as it stood was incomplete because it allowed for this strange, spooky action at a distance. Einstein was deeply uncomfortable with the notion that particles could influence each other instantly across vast distances. For him, the universe should be governed by locality, the idea that an object is only affected by its immediate surroundings. He believed there must be hidden variables, some deeper layer of physics not yet discovered, that would explain away the apparent strangeness of entanglement. Yet, over time, experimental evidence piled up that Einstein's intuition might not be correct. Physicist John Bell, in the 1960s, devised a way to test whether entangled particles behaved according to hidden variables or whether they truly operated under the bizarre rules of quantum mechanics. His theorem, known as Bell's inequality, provided a framework to test the predictions of quantum mechanics against classical expectations, and when experiments were carried out, starting in the 1970s and continuing with increasing precision into the 21st century, they consistently confirmed that entangled particles behave exactly as quantum theory predicts. They defy classical explanations and appear to share information in a way that transcends space and time. This discovery does not mean particles are literally sending signals faster than light. Rather, it suggests that the universe at a fundamental level does not conform to the classical idea of separateness. The particles are not communicating across distance. They are part of a single system, no matter how far apart they may seem. In other words, entanglement tells us that the boundaries we perceive between objects are not as clear, cut as we imagine. For many, this is the true mystery of entanglement. It forces us to rethink what reality even is. When we say two particles are entangled, it is tempting to think of them as two separate entities bound together by some invisible thread, but the more accurate way to describe it is that they are no longer two independent objects at all. They are a single quantum system described by one unified wave function. The separation we perceive in space is an illusion of perspective, while in the underlying fabric of reality they remain one. This realization has profound implications, not just for physics, but for philosophy and even our sense of existence. If the most fundamental building blocks of the universe can remain inseparably linked across cosmic distances, what does this say about the interconnectedness of the universe as a whole? Is everything, at some deep level, entangled with everything else? Could this principle extend beyond particles, hinting at a universal web of connection that underlies all reality? These are not just scientific questions, they are existential ones. The strange beauty of entanglement lies in its paradoxical nature. On the one hand, it is an invisible, intangible phenomenon. We cannot see entanglement with our naked eyes, nor can we fully grasp it in the way we understand more familiar forces like gravity or magnetism. Yet its effects are undeniable and measurable. In laboratories around the world, entangled photons are created and tested daily, and the results continue to confirm the predictions of quantum mechanics. In fact, entanglement has become such a reliable tool that it is no longer just a philosophical curiosity. It is the cornerstone of cutting-edge technologies. But before we explore applications, let us sit with the mystery a little longer. Imagine two astronauts traveling in opposite directions, each carrying one of a pair of entangled particles. One travels toward the distant reaches of the solar system, while the other returns to Earth. Decades later, when one astronaut measures their particle, the state of the other particle, trillions of kilometers away, is instantly determined. It does not matter that vast stretches of space and time separate them. The connection remains unbroken. To our everyday intuition, this is impossible. Information should not travel faster than light, and yet the particles seem to coordinate as though distance is irrelevant. Scientists still debate the exact meaning of this. Some interpretations of quantum mechanics, like the Copenhagen interpretation, simply accept that entanglement is a fundamental feature of reality and requires no further explanation. Others, like the many worlds interpretation, suggest that entanglement reflects the branching of parallel universes where measurement does not collapse a wave function but instead reveals one branch of a larger multiverse. Still others propose more exotic frameworks, hinting that entanglement might reveal hidden dimensions of space and time, or even connections to the fabric of spacetime itself. What unites these interpretations is the acknowledgement that entanglement cannot be explained away as a fluke or misunderstanding. It is real, it is measurable, and it is one of the deepest mysteries science has ever encountered. In many ways, entanglement has become the emblem of quantum mechanics, the phenomenon that best captures its strangeness and its promise. And while the mathematics of entanglement is precise, the human imagination struggles to keep up. We live in a world governed by locality and causality, where effects follow causes and nothing moves faster than light. Entanglement laughs at these rules, presenting us with a universe that is far more interconnected and holistic than we ever thought possible. It is as though the universe itself is whispering a secret, that separateness is an illusion, and beneath the surface, all things are bound together in ways we have only begun to glimpse. As we reflect on this, the definition of entanglement becomes more than just a description of particle behavior. It becomes a metaphor for the universe itself, a reminder that the deepest truths often defy common sense, and that mystery is not a barrier to knowledge, but a gateway to wonder. Quantum entanglement is not merely a scientific puzzle to be solved. It is an invitation to expand our understanding of reality, to embrace the unknown, and to marvel at the hidden threads that weave the cosmos into a single, unified whole. When Albert Einstein used the phrase spooky action at a distance, he wasn't simply trying to be poetic or playful. He was expressing a deep discomfort with one of the strangest predictions of quantum mechanics, one that seemed to threaten the very foundations of science as he understood it. To grasp why Einstein reacted so strongly to quantum entanglement, we must put ourselves in his shoes in a time when physics was undergoing a revolution and the very rules of reality were being rewritten. Einstein had spent much of his career showing that the universe operates according to elegant, universal laws. His theory of relativity had reshaped our understanding of space and time, revealing them not as rigid containers but as flexible, interconnected dimensions shaped by matter and energy. To Einstein, the universe was rational, predictable, and governed by principles that respected causality and locality. The idea that something could instantly influence something else far away went against everything he believed about how nature should work. In the early 20th century, quantum mechanics emerged as a powerful new framework for understanding the microscopic world of atoms and particles. It was incredibly successful in explaining phenomena that classical physics could not, such as the behavior of electrons in atoms or the way light behaves both like a particle and a wave. Yet, quantum mechanics also carried with it a strange and unsettling message. Particles do not have definite properties until they are measured, and when two particles become entangled, their properties remain linked no matter how far apart they are. For many physicists, this was simply part of the bizarre beauty of the quantum world. But for Einstein, it was intolerable. In 1935, along with his colleagues Boris Podolsky and Nathan Rosen, Einstein co-authored a paper that came to be known as the EPR paradox. The purpose of this paper was to highlight what he saw as a flaw in quantum mechanics. If the theory allowed for two particles to instantly affect one another across vast distances, then either information was somehow traveling faster than light, which contradicted relativity, or quantum mechanics was incomplete, and there must be some hidden variables, unknown factors that explain the correlation without requiring this spooky action. For Einstein, nature had to be local. In other words, an object should only be influenced by its immediate surroundings, not by something happening light years away. The universe, to him, could not allow instantaneous, faster than light connections. It was not just a scientific objection, it was a philosophical one. He often said that God does not play dice with the universe, meaning that he rejected the randomness and indeterminacy built into quantum theory. But quantum mechanics did not go away, and over time it grew stronger, supported by more and more evidence. Still, the question Einstein had raised lingered. Was entanglement a real feature of the universe, or was it simply a mathematical trick, a quirk of an incomplete theory? For decades, this debate remained unresolved. Many physicists, while respecting Einstein's genius, moved forward with the practical use of quantum mechanics because it worked so well, predicting experiments with unmatched accuracy, but they could not ignore the haunting puzzle he had left behind. Then came John Bell in the 1960s. Bell was intrigued by the EPR paradox and Einstein's objections. He devised what is now known as Bell's theorem, which created a way to test whether entangled particles behaved as Einstein imagined, with hidden variables preserving locality, or whether they truly acted according to the strange predictions of quantum mechanics. The beauty of Bell's work was that it turned a philosophical debate into a matter of experiment, and when those experiments were performed, first tentatively in the 1970s and with greater precision in the decades that followed, they consistently showed that Einstein's view was not supported by reality. The particles really did behave as quantum mechanics predicted. They remained entangled, their states correlated instantaneously in defiance of classical expectations. It is important to understand what this means. It does not mean that information is literally traveling faster than light, which would indeed violate relativity. Instead, it means that the universe does not operate under the classical notion of separateness. When particles are entangled, they are not two separate objects at all. They are part of one single quantum system. To measure one particle is not to send a signal to the other, but to reveal the state of the system as a whole. Einstein's phrase, spooky action at a distance, captures the sense of unease this caused him, but the deeper truth may be that there is no action at a distance at all, because there is no real distance at the level of entangled states. Space, as we experience it, may not apply in the same way to quantum systems. Einstein's discomfort resonates with us because it mirrors our own intuition. We live in a world where cause and effect are clear, where things here do not instantaneously change things there without some kind of connection or signal. His protest reminds us of how deeply unsettling quantum mechanics is, even to the greatest minds, and yet the very thing he resisted, the spooky action, has become one of the most important features of modern physics, one that is not only accepted but harnessed for revolutionary technologies. But let us pause for a moment and appreciate the courage it took for Einstein to challenge quantum mechanics at a time When many of his peers were embracing it wholeheartedly, he was not afraid to ask difficult questions, to point out paradoxes, and to hold on to his belief in a rational, ordered universe. Even though experiments eventually proved him wrong, his objections forced physicists to think more deeply, design better experiments, and to clarify their interpretations of quantum theory. In this way, Einstein's resistance helped strengthen the field he doubted. His phrase, spooky action at a distance, lives on as a reminder of the tension between intuition and reality, between what we expect nature to be and what it actually is. The irony is that while Einstein could not accept entanglement, it is now one of the very pillars of our understanding of the quantum world. Without it, quantum computing, quantum cryptography, and many other cutting-edge technologies would not exist. What Einstein once considered absurd is now the foundation of progress, but that does not diminish his legacy. Rather, it shows that even the greatest minds can struggle with the mysteries of nature, and that true science advances through debate, doubt, and the courage to question. When we reflect on Einstein's phrase, we can also see how it connects science to a broader human experience. His words capture the sense of wonder and fear we feel when we encounter something beyond our comprehension. Spooky action is not just a scientific puzzle, it is an invitation to marvel at a universe that is stranger than we imagined. It is a reminder that reality does not have to conform to our expectations. Instead, it challenges us to expand our understanding, to let go of rigid assumptions, and to embrace the unknown. Even now, physicists are still grappling with the full implications of entanglement. Some interpretations suggest that entanglement hints at a deeper layer of reality, perhaps one in which space and time themselves emerge from more fundamental connections. Others propose that entanglement might be the key to unifying quantum mechanics with general relativity, Einstein's own great theory. In a sense, the spooky action he resisted may hold the secret to completing the very vision he sought, a unified description of the universe. So when we repeat Einstein's phrase, we should not hear it only as a complaint or a dismissal. We should hear it as a challenge, a provocation, a call to explore further. For what is science if not the pursuit of the spooky, the strange, the mysterious? What greater honor could there be to Einstein's legacy than to continue asking the very questions he could not resolve, and to find in the spooky action at a distance the key to unlocking the universe's most profound secrets? In the end, Einstein's spooky action at a distance is both a warning and an inspiration. It warns us that our intuitions about reality may fail when we peer deeply into the quantum world. It inspires us by showing that even the strangest, most unsettling phenomena can become the seeds of new knowledge and new technology, and it reminds us that the universe is not bound by our comfort, but by its own truth. The fact that Einstein himself struggled with this truth makes it all the more human, all the more remarkable, and all the more worthy of our continued curiosity. Quantum entanglement is not only a scientific phenomenon, it is also a profound philosophical challenge. When two particles remain mysteriously connected across space and time, when their fates seem bound together no matter how far they are separated, we are forced to ask questions that go beyond physics and into the very heart of what it means to understand reality. Science often deals with measurement, prediction, and experimentation, but entanglement demands more. It demands reflection. It demands that we examine our deepest assumptions about individuality, separateness, causality, and the very fabric of existence itself. At first glance, entanglement seems like just another strange rule of quantum mechanics, one more curiosity among many in the strange subatomic world. Yet, when you look closer, you begin to see that its implications reach far beyond physics laboratories and equations. It forces us to confront the possibility that the universe is not built out of isolated parts, but out of relationships, that reality itself may not be a collection of separate objects, but a web of connections so intimate that distance and distinction dissolve when examined at their deepest levels. If that is true, then everything we think about identity, about independence, even about free will, takes on new meaning. Philosophically, entanglement shakes the foundation of reductionism, the idea that the universe can be fully understood by breaking it down into smaller and smaller parts. For centuries, science has followed this path, dissecting the world, analyzing its pieces, and assuming that the whole is nothing more than the sum of its parts. Entanglement says otherwise. It tells us that sometimes the whole is fundamentally different from the sum of the parts, that the relationship itself has reality, and that you cannot reduce it without losing the essence of what it is. Two entangled particles are not simply two objects with correlated properties, they are one inseparable system described by a single wave function. If you try to think of them as separate, you miss the point entirely. This insight has echoes in philosophy, in metaphysics, and even in spiritual traditions that have long emphasized interconnectedness. Consider the ancient idea that all things are connected, that the universe is one. Entanglement provides a scientific echo of this intuition, showing that at the deepest level, connection is not just metaphorical but measurable. It is not just a poetic idea, it is a physical fact. When philosophers speak of unity, they often do so in abstract terms, but entanglement grounds that unity in experiment and mathematics. It shows us that the boundaries we take for granted, between here and there, between me and you, between cause and effect, are not absolute but fluid. This challenges us to rethink identity itself. If two particles remain bound together, does that mean their individuality is an illusion? Does the concept of a separate self, whether at the level of particles or people, need to be re-examined? Some philosophers have suggested that entanglement is evidence of a relational universe, a universe where the basic unit of reality is not the object but the relationship. This is a radical shift from the way we normally think, but it may be closer to the truth. Entanglement also forces us to revisit the idea of causality. In the classical world, causality is straightforward. One event leads to another in a chain of cause and effect. Strike a match and the flame appears. Drop a stone and it falls to the ground. But in entanglement, causality becomes murky. Measuring one particle does not cause the other to change. Rather, the two outcomes are linked in a way that transcends the ordinary flow of cause and effect. Some interpretations suggest that both results were determined in advance by hidden variables, but experiments testing Bell's inequalities have largely ruled out that possibility. Others suggest that cause and effect may not be linear at all, but part of a deeper symmetry where time and space as we know them do not apply. This challenges us not only scientifically but philosophically. If cause and effect are not absolute, then how do we understand the nature of explanation itself? And then there is the question of reality. Quantum mechanics tells us that particles exist in a superposition of states until they are observed, and entanglement tells us that those states are shared across systems. But what does it mean to say that something is real if it is not definite until measured? Does reality exist independent of observation, or is observation itself part of what brings reality into being? Philosophers have wrestled with this for decades, and entanglement adds another layer of complexity. If two particles share one state, and that state is only revealed upon measurement, then the act of observing not only shapes one particle but defines both. In a sense, reality itself is not individual but relational. This has profound implications for how we think about consciousness. Some have speculated, controversially, that entanglement may even play a role in the workings of the mind, or that our awareness is somehow tied to the interconnectedness revealed in the quantum world. While such ideas remain speculative and often criticized, they reflect a deeper intuition that the mystery of entanglement is not just a puzzle for physicists, but a window into understanding our place in the cosmos. If the universe is fundamentally connected, then consciousness, too, may not be as isolated or individual as we imagine. Even if we leave aside speculation about consciousness, the philosophical impact remains. Entanglement suggests that the universe is holistic, not reductionist. It suggests that boundaries are constructs of perspective, not absolute truths, and it suggests that what we call separateness is, at best, an approximation. This raises ethical and existential questions as well. If everything is interconnected, what does that say about responsibility, about compassion, about how we treat one another and the world? In a purely classical universe where each part is isolated, one might imagine that actions affect only what is near, but in a relational universe where connections stretch across space and time, the idea of separation breaks down. Could it be that entanglement, beyond its technological uses, is a scientific reminder of our moral interdependence? This is why entanglement fascinates not only scientists, but also philosophers, poets, and spiritual seekers. It stands at the intersection of physics and metaphysics, bridging the measurable and the mysterious. It tells us that the universe is not a machine made of isolated gears, but a living web where each part is defined by its relation to the whole. To understand reality, we must not only study the parts but also the connections, and yet entanglement resists easy interpretation. For every philosopher who sees it as proof of unity, there is another who warns against overextending the metaphor. It is, after all, a physical phenomenon, not a mystical revelation. The danger lies in reducing its mystery to cliché, in forcing it to say more than it does. Still, even in its strict scientific sense, it forces us to wrestle with questions we cannot ignore. What is real? What is separate? What is connected? And perhaps most importantly, are we willing to accept that reality itself may be stranger, deeper, and more relational than we ever imagined? One way to appreciate the philosophical depth of entanglement is to consider the way it undermines our everyday experience. We live in a world where distance is real, where objects are distinct, and where time moves forward. Entanglement does not deny these things, but it reveals that beneath them lies a different order, one that does not conform to our senses. Philosophers have long argued that perception is limited, that the way we see the world is not the way the world truly is. Entanglement provides scientific confirmation of this. It shows that the categories of space and separation, which seem so obvious to us, are not fundamental but emergent. Beneath them lies a unity we cannot directly perceive but can measure. This calls to mind famous words of William Blake, who wrote of seeing the world in a grain of sand. Entanglement suggests that the whole universe may, in some sense, be present in each of its parts, not as a metaphor but as a physical reality. It invites us to see the cosmos not as a collection of scattered fragments, but as a single story woven together by invisible threads. And this is where entanglement becomes not only a scientific mystery, but a human one. For if the universe is interconnected at its deepest level, then perhaps so are we. Perhaps our sense of isolation, our insistence on separateness is an illusion born of limited perspective. Entanglement reminds us that reality itself is relational, and that to be is to be connected. Quantum entanglement is often spoken of as a mystery, a riddle of the universe that challenges the very foundations of our understanding. But what makes it even more fascinating is that it is not only a curiosity confined to chalkboards, theories, and philosophical debates. It is also a tool, an extraordinary, practical, and powerful resource that humanity is learning to harness. What was once dismissed by Einstein as spooky action at a distance has, over the past few decades, become the cornerstone of some of the most groundbreaking technologies ever imagined. It is one thing for a phenomenon to stretch our imagination, but it is another for that same phenomenon to lay the foundation of the future of computing, communication, and security. Quantum entanglement is doing exactly that. To appreciate its potential, we must first understand why it matters so much in technology. Traditional computers, for all their brilliance, operate within the classical framework. They process information using bits, each of which can exist in one of two states, 0 or 1. All of modern computing, every app, every website, every calculation, is built upon this simple binary system. But in the quantum world, particles can exist in a superposition of states. A quantum bit or qubit can be 0 and 1 simultaneously until measured. This alone vastly expands the computing possibilities. Now, introduce entanglement into the equation. When qubits are entangled, their states are linked, allowing for incredibly complex operations to be performed in ways classical computers could never achieve. The result is the possibility of quantum computing, a technology that could revolutionize the very fabric of human civilization. Quantum computers powered by entanglement are not just faster versions of today's machines. They represent a fundamentally new way of processing information. Problems that would take classical supercomputers millions of years to solve may be cracked by quantum computers in minutes. For example, simulating molecules at the quantum level is nearly impossible with current technology, yet such simulations could lead to breakthroughs in medicine, material science, and energy. Imagine being able to design drugs tailored at the atomic level, curing diseases with unprecedented precision. Imagine discovering entirely new materials with extraordinary properties, superconductors that operate at room temperature, batteries that store energy far more efficiently, or catalysts that make clean energy production practical on a global scale. Quantum entanglement is not just a theoretical curiosity here. It is the engine driving this possibility. But perhaps even more immediate than quantum computing is the role of entanglement in quantum communication. In the classical world, communication depends on signals traveling through wires, fiber optics, or airwaves, and those signals can be intercepted, copied, or hacked. Encryption protects us, but even the strongest codes can, in theory, be broken with enough computing power. Entanglement changes this. When two particles are entangled, information they carry is not stored locally in either one. It is shared between them as part of a single system. Any attempt to intercept or measure that system disrupts it, making eavesdropping immediately detectable. This is the basis of quantum cryptography, a form of communication that is, for all practical purposes, unbreakable. In a world where data is more valuable than gold, where cyber warfare is as real as physical conflict, entanglement offers the possibility of absolute security. Already, we are seeing the first steps toward this future. In 2017, China launched the Mission satellite, which used entanglement to establish secure quantum communication links between ground stations thousands of kilometers apart. This was the first demonstration that quantum communication is not just possible in theory but practical on a global scale. Other nations and private companies are racing to develop similar technologies, laying the groundwork for a quantum internet, a network where information is transmitted not through vulnerable signals but through the incorruptible bonds of entanglement. Such a network could revolutionize banking, government, military defense, and personal privacy, creating a level of security never before imagined. Beyond computing and communication, entanglement also offers possibilities in sensing and measurement. Quantum sensors, which rely on the delicate correlations of entangled particles, can achieve levels of precision far beyond classical devices. For example, entangled photons can be used in advanced imaging systems that peer inside the body or even into the Earth itself with extraordinary accuracy. They could help us detect gravitational waves with greater sensitivity, map underground resources without drilling, or navigate without relying on GPS, which can be jammed or disrupted. Entangled sensors might allow submarines to travel unseen or planes to navigate through hostile environments without external signals. In medicine, they could lead to imaging techniques that surpass MRI scans, providing real-time, non-invasive insights into the body at the molecular level. All of this shows that entanglement is not just a philosophical curiosity, it is a practical tool reshaping the future. And yet, the journey toward these technologies is not easy. Harnessing entanglement requires immense control over fragile quantum systems, which are easily disturbed by their environment. Quantum computers, for example, must operate at temperatures near absolute zero, and maintaining stable entanglement across large systems is an engineering challenge of staggering complexity. But humanity has never been one to shy away from challenges. The history of technology is full of breakthroughs that once seemed impossible: flight, electricity, space travel. And each time the impossible became reality. Entanglement is the next frontier, and we are already crossing its threshold. But the technological implications of entanglement also force us to ask deeper questions. If entanglement can be used to build unbreakable codes, what does this mean for governments and intelligence agencies that rely on surveillance? If quantum computers can break classical encryption, what happens to the security of today's digital infrastructure? If entanglement allows us to simulate entire molecules or materials, what responsibilities come with such power? The same technology that can cure diseases can also create weapons. The same communication systems that secure privacy can also empower secrecy on dangerous scales. As with every great leap, entanglement offers both promise and peril, and here philosophy and technology meet again. Entanglement is not just a tool to be exploited, it is a phenomenon that demands wisdom. We cannot simply harness it without considering the consequences. As we stand on the brink of a quantum revolution, we must decide how to use this power. Will it serve humanity's collective good, or will it deepen divides, concentrate power, and create new forms of inequality? These questions are not theoretical, they are urgent, and they will shape the decades ahead. Still, there is reason for hope. The very nature of entanglement, its insistence on connection, offers a metaphor for how we must approach its use. Just as entangled particles cannot be considered in isolation, so too must we not consider technology in isolation from ethics, from society, from humanity itself. If we remember that we are connected, that our fates are bound together just as those particles are bound, then perhaps we will use entanglement not only to unlock technological power, but also to foster understanding and cooperation. Imagine, for a moment, a world fully transformed By entanglement, hospitals equipped with quantum computers simulate diseases and design cures in days rather than years. Nations communicate securely without fear of espionage or cyber attack. Energy systems are powered by materials engineered at the quantum level, clean and abundant. Navigation systems guide us with precision even in the harshest environments, independent of satellites, and in every corner of the globe, people connect through a quantum internet that guarantees absolute privacy, where trust is built not on fragile codes but on the unbreakable laws of physics. This is not fantasy, it is the world entanglement makes possible, but the greatest gift of entanglement may not be the technologies it enables, but the perspective it offers. It reminds us that the universe is more connected than we imagine. It tells us that separateness is not absolute, that what seems divided can, in truth, be one. In using entanglement to build our future, we are not only harnessing a physical resource, we are embracing a deeper truth about reality. The challenge before us is to honor that truth, to use it wisely, and to ensure that the technologies it inspires reflect not only the brilliance of our minds but the compassion of our hearts. And so, as we look ahead to the quantum age, let us remember that entanglement is more than spooky action. It is a key that can unlock the most powerful technologies humanity has ever seen, but also a key that unlocks a new understanding of our place in the cosmos. It shows us that we are all bound together, not just by philosophy or metaphor, but by the very laws of physics. The question now is not whether entanglement will shape the future. It will. The question is, how will we shape the future with it? When scientists first discovered quantum entanglement, they were struck by its strangeness. Two particles, separated by vast distances, could remain mysteriously linked, their states mirroring one another in perfect harmony. Einstein himself, though skeptical, could not deny the evidence, calling it spooky action at a distance. But beyond its implications for physics and technology, there is something profoundly human in this phenomenon. It whispers to us about connection, about unity, about the unseen bonds that tie us together. For centuries, we have looked at the universe and seen separation between stars and planets, between people and nations, between body and soul. Entanglement challenges that view. It suggests that perhaps separation is an illusion and that on the deepest level, all things are connected. Think about the way we experience human relationships. We often feel connected to people across great distances, sometimes in ways we cannot explain. A mother knows when her child is in distress even if he is far away. Two friends pick up the phone at the same moment, each thinking of the other. Lovers, separated by thousands of miles, feel each other's joy and sorrow as if they were together. While science may not label these experiences as entanglement, in the strict sense, the metaphor is powerful. Just as particles once bound together remain linked no matter the distance, so too do human beings often feel bonds that defy space and time. This ideal becomes even more compelling when we consider our place in the cosmos. Every atom in our bodies was forged in the heart of a star. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was born in ancient stellar furnaces billions of years ago. We are not merely living on the Earth, we are made of the universe itself. Entanglement, in this sense, is not just a property of particles. It is a reflection of reality's deeper truth. We are participants in a grand cosmic web, not isolated observers standing apart from it. When we realize this, our perspective begins to shift. Imagine looking up at the night sky. To the naked eye, the stars appear scattered and alone, each shining independently. But the truth is, they are bound by gravity, by light, by the fundamental forces of nature. They are part of a larger whole, just as we are. Entanglement is like a cosmic reminder that what appears distant and disconnected is, in reality, linked. We are not separate from the universe. We are threads woven into its fabric. This understanding can change the way we see ourselves and one another. Too often, we live as if divided. We create borders, build walls, insist on differences that set us apart: race, religion, nationality, class. But if at the smallest scales of existence particles are united beyond separation, what does that say about us? Perhaps entanglement is a lesson in humility and compassion. Perhaps it teaches us that connection is the fundamental truth of existence and division is the illusion. Take a moment to reflect on what this means for relationships. Every interaction we have ripples outward, affecting others in ways we cannot always see. A kind word may brighten a stranger's day. A harsh word may wound deeply. Just as Entangled particles influence one another instantly. We too influence each other constantly. Our words, actions, and even our presence create connections that shape the lives of those around us. In this sense, entanglement is not only a scientific principle but also a metaphor for human responsibility. We are bound together and what we do matters. The cosmic perspective offered by entanglement also has the power to dissolve loneliness. How often do we feel isolated, adrift in a vast universe that seems indifferent? Yet entanglement reminds us that isolation is not the truth of existence. Even at the most fundamental level, nature insists on connection. No particle is ever truly alone. No human being is either. Our very existence is defined by relationships, parents and children, friends and communities, humanity and the earth and the cosmos. When we feel small under the infinite stars, entanglement tells us, you are not alone. You are part of something greater, inseparably woven into the universe itself. Consider also the spiritual resonance of this idea. Across cultures and religions, there have always been teachings of unity, of oneness. Mystics speak of the interconnectedness of all life, of the illusion of separateness. Indigenous traditions teach that the earth, the sky, the animals, and humans are all relatives bound in a sacred web. Eastern philosophies like Buddhism and Taoism emphasize interbeing, the truth that nothing exists independently but only in relation to everything else. Now, with entanglement, modern science echoes these ancient insights. It does not prove them in a theological sense, but it gestures toward a similar truth, that beneath the surface of things lies a unity that defies explanation. And what of love? Perhaps entanglement is the perfect metaphor for love. Two souls meeting and bonding remain connected even across time and distance. Love defies logic, it resists measurement, it binds people in ways invisible yet undeniable. In this sense, entanglement is not just about electrons or photons, it is about us. It tells us that the bonds we feel are not illusions, they are part of the fabric of reality itself. Love, like entanglement, is a force that transcends separation. On a larger scale, entanglement may reshape how humanity approaches the great challenges of our time: climate change, poverty, war, inequality. These are not isolated problems. They are entangled issues, each connected to the other. To solve them, we must recognize our interconnectedness. We cannot treat the earth as separate from ourselves, for we are part of it. We cannot treat one nation's suffering as irrelevant to another, for the fates of nations are bound together. If particles across the cosmos can remain connected, how much more must we, who share the same planet, acknowledge our entanglement with one another? This perspective also inspires hope, for if everything is connected, then no act of goodness is ever wasted. A single person's effort ripples outward, influencing others in ways unseen. Just as the state of one entangled particle instantly affects its partner, so too do our choices affect the collective. Entanglement is a call to responsibility, but also a call to possibility. It tells us that we are never powerless, for in the web of connection, every action counts. Now imagine the future of humanity shaped by this understanding. Imagine children being taught from a young age that they are not separate from the universe but part of its living fabric. Imagine education that emphasizes cooperation over competition, unity over division. Imagine politics guided not by narrow self-interest but by the recognition that the well-being of one is bound to the well-being of all. Imagine science and spirituality not as enemies but as partners in the search for truth, both pointing toward the reality of connection. Entanglement could be more than a scientific breakthrough. It could be a cultural and moral awakening. Of course, some may argue that drawing human lessons from quantum physics is merely metaphor, that the subatomic world does not dictate the human world. And they are right. Entanglement is a precise scientific phenomenon, not a mystical doctrine, but metaphors are powerful. They guide how we think, how we imagine, how we act. If the universe itself is connected in ways that defy space and time, why not allow that truth to shape our vision of life? The metaphor of entanglement may inspire us to see beyond our divisions and to embrace the deeper unity that sustains us. When we stand back and look at the grand sweep of history, we see that humanity's progress has always come from expanding our sense of connection. Once, people lived in isolated tribes, fearing outsiders. Over time, we formed nations, communities, and eventually global networks. Each step forward came from recognizing that we are part of something larger. Quantum entanglement may be the next great leap in that journey, not only scientifically but philosophically. It pushes us to see that our connections go deeper than we imagined, extending to the very fabric of the universe. And so, when we speak of unlocking the universe's secrets, we must remember that the greatest secret may not be in equations or experiments, but in what those discoveries reveal about ourselves. Entanglement shows us that reality is not built on separation but on relationship. It tells us that connection is more fundamental than distance, that unity is more powerful than division. It reminds us that while we may appear as isolated beings in a vast cosmos, in truth we are part of an unbroken whole. If we listen closely, the lesson of entanglement is simple yet profound. We belong to each other and we belong to the universe. To forget this is to live in illusion. To remember it is to live in truth. And perhaps if we take this truth to heart, we may find the wisdom to live with more compassion, more humility, and more love. So the next time you gaze at the stars, remember, you are not looking at something distant and foreign. You are looking at your own origin, your own family, your own self reflected in the cosmos. And just as those stars are bound together in a cosmic web, so too are you bound to every human being, every living thing, every atom in existence. This is the gift of entanglement, the reminder that we are not alone, not separate, not strangers in the universe. We are and always have been connected. When we speak of unlocking the universe's secrets, we are not just speaking of equations written on chalkboards, or the faint glow of galaxies caught through telescopes, or the quiet hum of machines buried in laboratories. We are speaking of something far greater, the quest of humanity itself to understand what it means to exist, to know why we are here, and to discover the hidden order beneath the apparent chaos of reality. Quantum entanglement, mysterious and unsettling as it is, stands at the threshold of this quest. It is not only a phenomenon in physics, it is a doorway, a key that may unlock truths about the universe far beyond what we imagine today. Throughout history, the greatest breakthroughs have often come disguised as mysteries. Electricity, once little more than sparks seen in the sky, became the power that lights our world. Gravity, once invisible and unexplained, became the law that describes the dance of planets. Entanglement is such a mystery today. It refuses to obey the ordinary logic of distance and separation. Two particles, once linked, behave as though they are one, regardless of how far apart they may be. Measure one, and you immediately know the state of the other. It is as if the universe is whispering, nothing is truly separate. Everything is bound together in ways you cannot see. If we can fully grasp this whisper, if we can decode what it means, we may uncover some of the deepest secrets of reality itself. One of the secrets entanglement points to is the very nature of space and time. For centuries, physics has treated space as the stage on which events happen and time as the clock that measures them. But entanglement challenges this view. If two particles, light years apart, can coordinate instantly, what does that say about the fabric of space and time? Perhaps space and time are not as fundamental as we think. Perhaps they emerge from something deeper, some hidden layer of reality where separation does not exist. Some scientists speculate that entanglement itself may be the thread from which space and time are woven. In other words, the universe might not be built of matter sitting in space, but of connections, relationships that give rise to the geometry of the cosmos. If this is true, then entanglement is not just a strange feature of quantum mechanics, it is the very foundation of reality. This possibility carries staggering implications. Imagine if space and time are not primary but products of entanglement. Then the universe is less like a collection of objects floating apart and more like an intricate tapestry of relationships. Unlocking this secret would not only reshape physics but philosophy, forcing us to rethink the most basic assumptions about existence. What does it mean to move through space if space is made of connection? What does it mean to live in time if time is born of entanglement? Questions that sound abstract today may one day guide our understanding of the cosmos as profoundly as Einstein's theories did in the last century. Another secret entanglement may unlock is the nature of information. At first glance, matter and energy seem to be the building blocks of the universe, but increasingly, scientists are discovering that information is just as fundamental. The way particles are entangled carries information that cannot be explained by classical means. Some theorists even suggest that the universe itself is a vast information processing system with entanglement as its operating principle. If so, then we are not only physical beings but informational beings, patterns written into the fabric of reality. This perspective may bridge the gap between mind and matter, offering new ways of understanding consciousness. Could it be that the awareness we experience, the thoughts and feelings that define us, are also part of this grand informational web, connected through principles similar to entanglement? If unlocking the Secret brings us closer to understanding consciousness, then entanglement does not just explain particles, it explains ourselves, but the secrets entanglement holds are not confined to abstract questions. They touch practical frontiers as well. Consider the possibility that entanglement may one day allow us to harness entirely new forms of communication. Already, quantum communication promises security beyond anything classical methods can provide. But what if entanglement could transmit not just cryptographic keys but entire streams of information? What if communication could happen not at the speed of light, but instantaneously because it bypasses space altogether? The implications for space exploration alone would be revolutionary. Today, sending a signal from Earth to Mars takes minutes and to the edge of the solar system hours. But if entanglement can be harnessed for instantaneous communication, then distance becomes irrelevant. Civilizations could remain connected across interstellar distances, building a cosmic community without the barriers of space. To unlock this secret would be to shrink the universe, binding its farthest reaches into a single, living whole. There is also the secret of unification. For over a century, physics has been divided between two great theories: quantum mechanics, which describes the smallest scales of atoms and particles, and general relativity, which describes the largest scales of stars and galaxies. Both are spectacularly successful in their domains, yet they refuse to reconcile with each other. Somewhere, hidden in the fabric of the universe, lies the key to unifying them. Many physicists suspect that entanglement may be part of that key. If space and time emerge from entanglement, then gravity itself, the warping of spacetime, may also emerge from quantum connections. This means that the path to a theory of everything may run directly through the heart of entanglement. To unlock this secret would be to finally complete the greatest scientific quest of all: the unification of the laws of nature into a single, coherent picture. But even beyond science, entanglement holds secrets that touch the human spirit. It speaks to the unity of existence in a way that resonates with our deepest intuitions. We often sense in quiet moments that we are part of something greater. Entanglement suggests that this intuition is not mere poetry but perhaps an echo of reality. It tells us that the universe is not a machine of isolated parts but a living whole where each part reflects the other. This has profound implications for how we see ourselves, not as solitary beings adrift in a vast cosmos, but as threads in an intricate cosmic web. If we unlock this secret and truly internalize it, it may change how we live, with greater compassion, humility, and reverence for the connections that bind us. And yet, as with all great keys, the power of entanglement demands responsibility. Unlocking secrets is not enough. We must also decide what to do with them. The technologies born of entanglement, quantum computers, quantum communication, quantum sensing, hold immense promise but also immense risk. They could heal or harm, unite or divide, uplift or oppress. The real secret of universe may not only lie in understanding how it works, but in learning how to use that understanding wisely. Science can give us the key, but only wisdom can guide how we turn it. Still, when we look at entanglement, we cannot help but feel awe. It is as if the universe has left us clues, like footprints in the sand pointing toward a deeper reality. The particles we study in labs, the photons fired through fiber optics, the atoms cooled to near absolute zero, these are not trivial things. They are hints, whispers of truths waiting to be unveiled, and as we unlock them, we are not only uncovering secrets about matter and energy, we are uncovering secrets about ourselves, about what it means to be conscious beings in a universe that is conscious of itself. So what lies ahead? Perhaps one day we will look back at our era and see it as the dawn of the quantum age, the moment humanity first grasped the significance of entanglement. Perhaps in the future, people will travel through space using technologies built on quantum principles, communicate across galaxies through entangled networks, and simulate entire universes within quantum computers. Perhaps they will unlock mysteries of black holes, dark matter, and dark energy, using entanglement as their guide. Perhaps they will even understand consciousness itself as an emergent property of entangled information, dissolving the mystery of mind and matter into a single, unified truth. But even if those possibilities lie far ahead, we are already changed by what we know today. The discovery of entanglement has cracked open the door to the universe's secrets. It has shown us that reality is stranger, deeper, and more beautiful than we ever imagined. It has reminded us that the greatest treasures are often hidden in the smallest things: particles too tiny to see, connections too subtle to grasp, truths too profound to ignore. And so, as we stand on this threshold, Let us recognize the privilege and the responsibility of holding such a key. We are explorers of the infinite, seekers of the unknown. Participants in the unfolding story of the cosmos, each discovery we make is not just a step in science, but a step in our journey toward understanding who we are and what we are part of. Entanglement may be mysterious today, but tomorrow it may reveal the very architecture of reality. It may unlock the secrets of space, time, information, and mind. It may show us that the universe is not simply a place we inhabit, but a living network of connection of which we are inseparably a part. Unlocking the universe's secrets is not just about knowledge, it is about awakening, it is about realizing that we are not separate observers looking at the universe from the outside, but participants woven into its deepest fabric. Entanglement, strange and wondrous, is the key that brings us closer to this realization. And as we use it, not only to build technologies but to expand our vision, we may come to see that the greatest secret of all is not that the universe is knowable, but that the universe is us.